What is good, everybody? Welcome back to another episode. So last time we finally managed to build the arithmetic logic unit. So that's basically a full-on calculator. We can give it instructions to add, subtract, and even do comparisons with conditionals. But one of the cornerstones of computing, at least modern computing, is the computer can remember things, and that's what memory is. I am aware that modern calculators can also remember basic things, but I'm talking about like remembering complex things like variables, databases, persistent state, all of that. And we need to be able to make our hardware remember things. So that's what we're going to cover in this video. So let's get started with the SR latch. So the SR latch holds 1 bit. Basically, it uses a interesting quirk of physics to kind of hold a bit until you reset. Let's see how it works. So when the set bit is 1 and the reset is 0, then you want to set it to 1. Otherwise, if you set the reset to 0, I know there's a lot of set and resets, but basically if you set reset to 1, then it clears it. If you set both to 1, then nothing happens, and then it's undefined if you set both to 0. So basically nothing happens, so yeah. So what we're going to do is we're going to build this circuit by using just 2 NAND gates. And notice what I'm going to do with it. First, I'm going to feed in S to this NAND gate and then R to this NAND gate. And then notice that I'm going to feed the output of this NAND gate to the input of this NAND gate. And similarly, I will feed the output of this NAND gate to that NAND gate. So it's kind of like they're feeding into each other. And what this does is that once I press S here, it will set this. But then when I stop, it kind of creates this feedback loop. And it just kind of like continually feeds off of each other. And it kind of remembers that we have a 1. And then obviously if we clear it, boom, set that to 0, that kind of clears everything. And then, yeah, so basically we're going to just feed this into the output like that. And then let's check for solution. And there we go. This is optimal. So yeah, a very basic latch. All right, let's go on. So the next latch that we're going to build is the data latch or the D latch. So this is building off again the very simple SR latch, which can just do one thing at a time. It's adding some more values. So when the store bit is 1, the value on D is held and emitted. When the store is 0, then the value of D is ignored and the previously held value is still emitted. So this is kind of like SR latch, but you can kind of see there's a interesting behavior with how you store one thing and then how you actually access one thing. So we're just going to use the SR latch for this, but then we're going to add a few more things. So we're going to need our 2 NAND gates back again because we're trying to emulate this behavior. So we have these 2 NAND gates, and then what we're going to do is we are going to get an inverter right here, and then we're going to get our data to be inverted into this NAND gate. And by the way, this NAND gate is the set because we're setting data, and you'll see why we do an invert later. But what we're going to do is this store bit will basically go to this NAND gate and also this NAND gate. And then finally, data will also go to this NAND gate. So again, this kind of like complementary behavior. What we're going to do is when we set this 1 and D is 0, output should be 0. When we set both to be 1, you can see it's 1. But when we're setting S to 0, now you can see that unlike the SR latch where you need to reset something, it's just basically saying I'm read only now. So this is reading data only. We can't write to it. No matter what you do, it's stuck on 1. If you set S to 1, now it's write available. So we can write to the data. You can see it's just toggling back and forth. But once again, read only, store to 0, boom, nothing happens. Actually, let's just make this 0 just so you can see that it's just nothing happens. And these NAND gates are controlling this, kind of like a mux with the inverter and stuff. So yeah, that's the difference between the data latch and the SR latch. Kind of subtle, but very important for the next component. So let's check the solution. Yep, and this is optimal. Alright, is at this point, we're going to use a component that needs a clock. And a clock is basically just a signal that toggles back and forth between 1 and 0. So I'm going to emulate a clock for you. There we go. Just 1, 0, 1, 0 at a fixed rate. And we're not going to be able to build a clock in NAND game, mainly because it requires some complicated chemistry and physics to make it oscillate. So that's something you guys can learn yourself once you go into the computer engineering field. But I just want you to know that we're going to need a clock to build what's known as a data flip-flop or a D flip-flop. And this is a very important component because the clock can kind of start updating things. This is the first time where we can start updating state. Because again, latch, we had to use our own set and reset. So SR latch, set and reset. D latch, we had to do the store bit to make it read only. All of that needs to use manual intervention. But this time we're going to use the clock, and the clock is kind of going to automatically control all of that. So what we're going to do is we're going to need a mux. We're going to need a D latch. Because again, data flip-flop is based off of the data latch. And then we are going to get the NAND gate. And then this NAND gate is going to control partly the clock and the store bit. Again, I kind of alluded to that, where the clock is kind of like responsible for updating it at an incremental amount of time. And then the select bit, we just feed in this select to be the NAND gate. And then this will also go to store. So the store bit will also go to NAND. And then this data will go here. But then notice we're going to feed the feedback back into the select component, because what we're going to do is we are going to essentially use the clock to kind of like update this and toggle it back and forth. And let's try it. So right now, nothing's happening yet. Even if we want to set D to 1 and we enable writing, because we need to pulse the clock. So boom, clock pulse, now it's 1. And now we're going to make it read only. So no matter how much the clock pulses, you can see this NAND gate is kind of controlling that and blocking it. And again, you might ask, why can't we just, toggle the set bit ourselves? Why need a clock? That's because we need to synchronize everything to make sure everything's on the correct state before we continue. Otherwise, you get stuff like race conditions where some things get updated quicker because they have less transistors, and it gets messy. So that's why we need a clock to keep everything in time. Alright, let's check solution. So this is the fewest possible components, but it is possible to solve with a lower total of NAND gates. So again, that's the challenge. Up to you guys. See if you guys can make it better. But yeah, let's go on to the next level. Okay, so I talked about how the data flip-flop is very important because you can see it kind of uses the clock to store stuff and update stuff. And we're going to now get into what's known as a register. Yes, this is the CPU register that you always hear of. We're going to talk about assemblies, so like RAX, RBX, RSI, all of that will come later on in this playlist. But for now, we're just going to build a hardware register, which is basically data flip-flop, but instead it stores any number of bits instead of just 1 bit, because the data flip-flop only stores 1 bit. We're going to build it for 2 bits. As always, NAND game will extend it to 16 bits, or I guess in your machines there will be 64 bits per register. So to do that, we're just going to store 2 bits instead of 1. So all we need is just 2 data flip-flops. That's it. So clock, and this, by the way, this is where clock comes useful, because now you can see it synchronizes both of them at the same time. So this data flip-flop won't basically get ahead. It'll wait because the clock has to update. Then this data flip-flop will have to update as well. So that's why you see the clock starts to become useful once we get into stuff like registers. Even though it can be accomplished with latches, but again, the timing is just weird. So just goes to D0, this goes to D1. This is probably one of the more basic levels in a while, probably since like, I don't know, like the AND gate in, by the way, all the way in episode 1. So this is, yeah, there's not even any test. You can kind of see how it works. Alright, so now we have a register that can store stuff when the clock updates. So next, we're going to talk about what a counter is, because as we're going to go through CPU instructions, we need to be able to move the instruction pointer and run instructions. When you're reading a recipe, you want to count down the recipes. You want to go step 1, step 2, step 3. So that's what the counter does, but except for in a CPU level. So yeah, even they say counters are a core component because they actually execute the instructions, because you won't be able to go to the next instruction without the counter adding 1. So this is why we also did the increment by 1 thing all the way back. So to do that, once again, if the store is 0, then set next output to 1, and otherwise set next to X. By the way, why do we want to set something to X? That's because we want to do jump statements where you can kind of create loops and stuff. So again, this is coming later on, but hopefully it will make sense when we talk about jump instructions in assembly. So first thing we're going to do is we definitely need a register to keep track of what we're kind of doing, our current value that we're trying to count. And then we need a mux. This mux is going to select between two things. So it's going to either increment 16 or it's going to use the X value. So it's going to just override that instruction address. Clock obviously goes to the register directly. And what we're going to do is we're going to get a 0. We're going to invert that 0. Again, what happens when we invert ground? We get a constant voltage source, or basically true value always. And then this guy goes to be the register set. That is because we want it to always set unless something happens with this select statement, which you'll see here. So clearly this will be the output. So let's connect that first. And then X will be basically the input of the selection. And then what we'll do is we'll feed the output of the register into that increment so that whatever X was beforehand, boom, comes out, go through the increment, it adds 1, gets selected, puts it back in. And then finally, well, yeah, we also have to get the store bit to control this mux between X or next output plus 1. That should be it. Let's just test it. Let's just say we're going to run an instruction at hex value 64 or decimal 100. And then you can kind of see when we toggle the clock, it starts counting forwards, but it starts back at 0. However, if we set it, then it starts at 64 or X, and then when we set it off, it continues from X, and that's how you implement the jump statement. So again, you can see the clock is kind of controlling everything. So let's check solution. And this is the simplest possible solution. So 738 NAND gates. Hopefully you guys didn't try to actually find the shortest way, because yeah, that is going to be a lot of NAND gates. All right, we're on to the final level now. At least final level in this section. So the last thing we're going to build is RAM. And you might have heard of RAM before. The last few things we've built isn't really RAM because we can't address them. We have some flip-flops, we have registers, but they're just single values. We kind of saw how we can use counters to step through addresses, but now we want to be able to randomly access anything. So we give it address, whatever it is, it finds it. So that's what RAM is. That's why your computer is so fast compared to like the ancient computers. So let's start with building the RAM. So we have address indicates which storage unit we're accessing. So right now, again, we're only building a RAM with 2 units, which might seem dumb, but we're going to be able to extend it to however many, like 32 gigabytes. That's 32 billion bytes, 32 billion units, all of that. We're just going to do it for 2 just to prove that it kind of works. So we need 2 registers, of course, because each register stores data. So these are like our data banks, data pools. We're going to need a switch statement, and this guy will go to select as data. Address will be S, and then we also need a mux up here or a select statement, and then this select will be controlling the address, and then you can kind of see where this is going already. So this will be the output. This mux is controlling. This is register 1 or address 0. Address 1. This is address 0. So we have 2 addresses, and then finally, we just feed in X to both of them, and then just kind of toggle depending on which one you want to store. So that's why this is C0, and then this is C1. So the switch statement kind of, again, toggles, and then clock goes to the common clock. And you can kind of see clock is controlling everything, kind of orchestrating the band here. So let's just test it out. We want to set 5340 to address 1. So this guy right here. So this guy should remain 0. This guy should remain 1. Again, nothing happens yet. Boom. Clock. I guess this is 1. Okay. Let's see if I did this wrong or not. Let's check solution. Nope. I did not do this right. So we just gotta switch it back. Like that. Alright. So yeah, we found out through testing that this guy's 1 and this guy's address 0. So now this should work. Yep, and there we go. That finishes the memory unit. Now you kind of know how computers can store data. And not only that, access data randomly, which is what RAM is. And then finally, most important of all, we've introduced the clock. And the clock only will come back again and again through stuff like interrupts, and then like control unit, a CPU cycle. Like the clock will just remain here. It's just a core component. I know I didn't explain what it is, but again, it involves some complicated chemistry with like crystals and how it vibrate. So you can research that on your own. But hopefully you enjoyed this video. Please leave a like and subscribe, and I'll see you in the next one.